Hello viewers, in my previous two lectures I have been discussing synthetic applications of ethyl acetoacetate, where we had discussed preparation of monocarboxylic acids and dicarboxylic acids. Continuing in the same vein, today I shall be discussing synthesis of alpha-beta unsaturated acids, beta ketonic acids and ketones. So let us start with synthesis of alpha-beta unsaturated acids. What do we mean by an unsaturated acid? An unsaturated acid is an acid where there is double bond between two carbons or a triple bond between two carbons. And what do we mean by alpha-beta? When this double bond or triple bond is between the alpha carbon and the beta carbon, the molecule is known as alpha-beta unsaturated acid. For synthesis of alpha-beta unsaturated acids, I shall be discussing with you synthesis of crotonic acid. For this synthesis, we shall be using Norman-Nagel condensation reaction, in which a reactive methylene compound is treated with an aldehyde or a ketone in presence of a dilute base, resulting in followed by acidic hydrolysis, resulting in formation of alpha-beta unsaturated acid. So when we are discussing crotonic acid, for this we shall treat ethyl acetoacetate with acetaldehyde in presence of a weak base like pyridine or diethylamine, which will be used as a catalyst. And this reaction will give us an alkylidene derivative of ethyl acetoacetate, which on acidic hydrolysis will give alpha-beta unsaturated acid. So let us see what shall we do for this reaction. In this case, we are treating ethyl acetoacetate with acetaldehyde in presence of pyridine, and you can see the reaction on your screens. When we do so, we get an alkylidene derivative of ethyl acetoacetate. Alkylidene means that the two functional groups are attached to the same carbon, which you can see on your screens. So when we carry out the acidic hydrolysis of this alkylidene derivative of ethyl acetoacetate, crotonic acid is formed. So what happens, if you recapitulate, when we carry out the acidic hydrolysis, the OH, we will bring about this reaction with the help of two molecules of water, and one molecule will add in such a manner that its OH will go to the acetyl group, that is the carbonyl group of the acetyl group, and hydrogen will go to the methylene group, resulting in the formation of acetic acid, which will be your side product. And then a bond is cleaved between the carbonyl group of the ester group and the ethoxy group. In this case, again the OH will go to the carbonyl group of the ester group, because the carbon of the core carbonyl group is electron deficient, and H plus will go to the ethoxy group, resulting in the formation of ethanol. And the central part of the molecule will be converted into crotonic acid, which is CH3 CH double bond CH COOH. The IUPAC name of this molecule will be but-2-enoic acid. Because we will give priority to the carboxylic group, it will get number 1, and the double bond is getting number 2. That is, double bond is between second and the third carbon. So the name will become but-2-enoic acid. Now let us discuss the preparation, or let us now discuss the mechanism of the reaction. So when we look into the mechanism of the reaction, what happens in this case, we are taking a weak base like pyridine. We will not take a strong base here, because if we take a strong base here, then what can happen is self-aldol condensation can take place. That is, two molecules of acetaldehyde will react among themselves to give us a aldol. So we want to avoid that reaction. So therefore what we do is we use a weak base like pyridine. So as you can see on your screens, in the first step, pyridine abstracts a proton from ethyl acetoacetate, resulting in ester anion. And this ester anion, in which there is negative charge on the methylene carbon, will act as a nucleophile. And in the process, we get a pyridinium cation. Now in the next step, the nucleophile will make a bond or will attack the carbonyl carbon of acetaldehyde, because the carbonyl carbon of acetaldehyde is electron deficient. As oxygen is more electronegative, it will pull the electrons towards itself. So as a result of this, we will get a addition compound or addition product. That is, a bond will be formed between the methylene carbon, that is the negative charge on the methylene carbon of ethyl acetoacetate, which is acting as a nucleophile, and the bond will be formed between the methylene carbon and the carbonyl carbon. And what do we observe? That the intermediate that we are getting here has a negative charge on oxygen. Now again, in an acid-base reaction, pyridinium cation, or in other words, will donate a proton, or in other words, what we can say is that this addition intermediate that we've got, anion that we've got, in which there is negative charge on oxygen, will pick up a proton from pyridinium cation, resulting in the product. Now what we find in next step is that this intermediate, that is we've got here, will lose a water molecule, and when it loses a water molecule, it will result in the formation of alkylidene derivative of ethyl acetoacetate, which again you can see on your screens. So what happens in this case is that is O, being more electronegative than carbon, will pull the electrons towards itself, as a result of which the bond between the carbon and the hydroxyl group will become weak. And at the same time, this oxygen, now the bond between the methylene carbon and hydrogen will become weak. Why will this become weak? Because the methylene carbon is sandwiched between electron withdrawing groups. So as a result of which this carbon, methylene carbon, will have a slight positive charge on it. So in other words, we can say that OH will pick up a proton, and the bond between the methylene carbon and the hydrogen will end up forming a double bond between the methylene carbon and the carbonyl carbon. When this happens, what are we getting now? We are getting alkylidene derivative of ethyl acetoacetate, where there is a double bond between the methylene carbon and the carbonyl carbon of acetaldehyde. In the next step, we will carry out the acidic hydrolysis. And when we bring about acidic hydrolysis, you know that this hydrolysis will be brought about by two molecules of water, and as you can see on your screens, one water molecule will break in such a manner that the OH group goes to the acetyl group, and we will get acetic acid from there, and the hydrogen will go to the methylene carbon. And on the right hand side, the bond between the carbonyl group of the ester and the ethoxy group will break in such a manner so that the OH goes on to the carbonyl group of the ester and proton goes on to ethoxy group, again resulting in formation of ethanol. And the central part will give rise to crotonic acid. So this is the mechanism of formation of crotonic acid, that is alpha beta unsaturated acid from ethyl acetoacetate. Now the next important reaction that I would like to discuss with you is that of synthesis of beta keto acids. So when we talk of a beta keto acid, that means, now if you remember, when we carry out the ketonic hydrolysis of say ethyl acetoacetate, there we get acetone, carbon dioxide and ethanol. That is, ketone is formed in that case. And when we are carrying out acidic hydrolysis, we get a molecule of acetic acid, we get two molecules of acetic acid and a molecule of ethanol. Now what we want to prepare is, we want to prepare beta keto acids. That is, we want to prepare a molecule where we have a keto group and the carboxylic group in the same molecule. And we know if we bring about ketonic hydrolysis, we will get a ketone, and if we do an acidic hydrolysis, we will get an acid. So what should we do? So the first step would be that we introduce the acyl group in ethyl acetoacetate. Right? So what are we going to do? We are going to add our CO group, that is acyl group, to ethyl acetoacetate for the synthesis of beta keto acid, that is 3-oxobutanoic acid. So first of all, what are we going to do? The first step, please remember, in all the synthetic applications is, in most of them we will be converting ethyl acetoacetate into its sodium salt. So if you look at the screens again and concentrate there, we are treating ethyl acetoacetate with sodium ethoxide. When we are doing so, we are getting sodium salt of ethyl acetoacetate. And this sodium salt on ethyl acetoacetate, on reaction with acetyl chloride, gives us, or it introduces another acetyl group in the ethyl acetoacetate. So what do you find? When we carry out this reaction, that is reaction of sodium salt of ethyl acetoacetate with acetyl chloride, another group, that is COCH3 group, is introduced. So if you look at the molecule now carefully, what do you find? That the central carbon, the original methylene carbon, is attached to two aceto groups and one ester group and a reactive or an acidic hydrogen. So what are we going to do here? We want to prepare a keto acid, right? So what do you think you will do here? Acidic hydrolysis or ketonic hydrolysis? We already have, if you look into in the molecule, we already have two aceto groups here. We do not have a acidic group here. So how can we get an acidic group here? If we carry out acidic hydrolysis, what will happen? Hydrolysis of ester will take place and that group will be converted into a carboxylic group. But our aim is that we just need one aceto group. So what we'll do is, we will bring about acidic hydrolysis. And you know, when we are carrying out acidic hydrolysis, we carry it out with two molecules of water. So when we carry out the reaction with two molecules of water, as you can see on your screens, that is what will happen now. One molecule will add in such a way, of water will add in such a way that the OH group goes to the acetyl group and the H goes to the methylene carbon, and acetic acid will separate out. And then when we add second molecule of water, you know how will it add? The OH will go to the carbonyl group of the ester and proton will go to the ethoxy group, and in the process ethanol will be eliminated, and again the central part of the molecule will be converted into 3-oxobutanoic acid. And why do we call it as a beta acid? Because beta keto acid, we can say that the ketonic group is at the beta position, that is methylene carbon is the alpha carbon, the carbonyl group is the beta carbon. Or you can say that the CH2 group is separating a carbonyl group and a carboxylic group. Now let us discuss the synthesis of ketones. Till now I have discussed with you synthesis of monocarboxylic acids, dicarboxylic acids like succinic acid and adipic acid, unsaturated acid like crotonic acid, and a beta keto acid. Now let us start with the synthesis of ketones. For this we shall be discussing ketones, synthesis of ketones as well as diketones. So first, when we talk of synthesis of ketones, for that I would like to discuss with you synthesis of 3-pentanone. So for this, as I've already said, that whenever you're bringing about synthesis, the first reaction or the first step that you're going to do in the reaction is to convert ethyl acetoacetate into its sodium salt. And when we are doing this, if you recapitulate this reaction, and we are not converting ethyl acetoacetate into its sodium salt, we are simply doing its ketonic hydrolysis. So what you have to remember is that when we do ketonic hydrolysis, we will add one water molecule to ethyl acetoacetate. Whereas when we prepare a carboxylic acid, then in that case we are carrying about hydrolysis with 2 water molecules. So when we are bringing about adding 1 water molecule, or we are breaking the bonds with the help of 1 water molecule, what you have to remember is that hydrogen will go to the methylene carbon, oxygen will go to the carbonyl group of the ester, and then hydrogen will add as a proton to the ethoxy group, resulting in the formation of ethanol. That means from the basic unit of ethyl acetoacetate, we will get 1 molecule of acetone, 1 molecule of carbon dioxide and 1 molecule of ethanol. And now you want to prepare 2-pentanone. So how many carbons are we getting if we were carrying out hydrolysis simply of ethyl acetoacetate? Without converting it into its sodium salt, we are getting acetone. Now in this case, I am saying that you want to prepare 2-pentanone. So how many carbons are we short of? We are short of 2 carbons. So in that case, we will bring about reaction, say, with ethyl bromide. So let us now look into the synthesis of 2-pentanone. So what is your first aim going to be? You are going to convert this ethyl acetoacetate into its sodium derivative. And when you do so, you will bring about the reaction of sodium salt of ethyl acetoacetate with ethyl bromide. And when you treat it with ethyl bromide, you will get alpha ethyl derivative of ethyl acetoacetate. That is what we've done first is we've converted ethyl acetoacetate by treating it with sodium ethoxide into its sodium salt. And then we are treating sodium salt of ethyl acetoacetate with ethyl bromide, when we are getting alpha ethyl derivative of ethyl acetoacetate. And now this derivative or ketonic hydrolysis will give you 2-pentanone. So let us now see first I have summarized the reactions for you, which you can see on your screens, and then we will go into the mechanism of the reaction. So in the first step, you are going to treat ethyl acetoacetate with sodium ethoxide when it will be converted into its sodium salt. You will treat it with ethyl bromide when it will be converted into alpha ethyl derivative. Then you will bring about reaction with dilute KOH followed by acid hydrolysis. When you do so, you will get 2-pentanone. So these are the series of reactions that you are going to write 1, 2, 3 and 4. This is the order in which we are carrying out the reactions. Now let us see how the mechanism will take place. In the first step, as I have told you, that ethyl acetoacetate will be treated with sodium ethoxide and you will get sodium salt of ethyl acetoacetate, which you can see on your screens. Now this sodium salt of ethyl acetoacetate will react with ethyl bromide. We have a negative charge on the methylene carbon. Since we have a negative charge on methylene carbon, this will act as a nucleophile from here. And in ethyl bromide, bromine being more electronegative than carbon will pull the electrons towards itself. As a result of which, this carbon will have a positive charge. So what will happen now? The nucleophilic methylene carbon, through its negative charge, will make a bond with the electrophilic carbon of the ethyl group, and NABR will be eliminated in the product. Now what will we get here? We will get here monoethyl derivative of ethyl acetoacetate. Now I want to add something here. Supposing we were just preparing 2 pentanone. If we were given that you have to prepare 3-methyl pentanone, what would you do in that case? In that case, please remember, after this stage, after the preparation of ethyl derivative of ethyl acetoacetate, you will again bring about reaction with sodium ethoxide, convert it into its sodium salt, and then bring about the reaction, say, with methyl bromide or whatever alkyl group they are asking you to introduce, and then we will get a substitution here, and after that we will bring about the ketonic hydrolysis. Now let me say that I am going back again to 2-pentanone. So when we are not talking of 2-pentanone, after we've done this, we've prepared the monoethyl derivative of ethyl acetoacetate. What will happen? We'll carry out the ketonic hydrolysis. And you know, when we bring about ketonic hydrolysis, what will happen? Proton will go to the methylene carbon, oxygen will go to the carbonyl group of the ester, and H will, as a proton, will go to the ethoxy group. So we will get 2-pentanone as the major product, and carbon dioxide and ethanol will be the side products. For this lecture, I had discussed the books by Bell and Bell and Morrison and Boyd. In my next lecture, I shall be discussing with you preparation of diketones and heterocyclic compounds. Thank you.